Hello everyone, this is another Math 101 lecture. Here we're going to move backwards a little bit in our course just to finish off a few topics that I left unfinished in number theory. So this one is prime numbers, perfect numbers. It's perfect numbers is a topic that goes under prime numbers, and so it goes under number theory, but it's something that I skipped earlier in the course, so I'm going to try to finish it off right now. So, perfect numbers, the concept of perfect numbers and related concepts come from Greek numerology. And numerology is sort of the study of superstitions around numbers. But there still is some interesting mathematics that survives. I mean, the numerology is long gone, but the mathematical theorems still survive. And it's believed that this topic probably comes from the Egyptians and is related to the Egyptian way of writing fractions. And that makes it one of the oldest unsolved problems in mathematics. So just for that reason, the study of perfect numbers can be kind of interesting. So let's take a look at some examples. First, we're going to look at some numbers that are not perfect, and then we're going to look at some numbers that are perfect, just to see what the relevant property is. So let me take the number 10, and what I want to do is to write down all the divisors of 10. In order to do that, remember, we can find the prime factorization of 10, and that always gives me a table. For 10, it looks like this. So 1, 2, 5, and 10. So the divisors of 10 are 1, 2, 5, and 10. Now we're going to introduce a very simple additional concept, the proper divisors of 10. And those would be 1, 2, 5, and not 10. So proper divisor means every divisor except the number itself. So when I'm talking about the number 10, 10 is a divisor of itself, but it's not a proper divisor. So that's really just a very simple concept. We just remove the number itself from the list of its divisors. So the proper divisors of 10 are just 1, 2, and 5. And now what we're going to do is add up those proper divisors. 1 plus 2 plus 5 is equal to 8. And that is the sum of the divisors of 10. The sum of the proper divisors of 10. All right, so that is a process that we're going to go through repeatedly for different numbers. Now notice that 1 plus 2 plus 5 is actually less than 10. And so the Greeks had a word for this. They called 10 is deficient. Meaning the sum of its proper divisors is less than the number itself. Okay, so let's take a look at another number, our friend 12. We have the factorization, which you can do. 12 is 2 to the power 2 times 3 to the power 1. Divisors are by this table. This is all very familiar to you, I'm sure. 1, 2, 4, 3, 6, and 12. So the divisors of 12 are 1, 2, 3, 4, 6, and 12. And the proper divisors of 12 are 1, 2, 3, 4, 6, and not 12. So there are 5 proper divisors of 12. Let's look at what happens when we add them up. 1 plus 2 plus 3 plus 4 plus 6, and that is equal to 16. That is bigger than 12, and so we say 12 is abundant. So 10 is deficient. The sum of its proper divisors is less than 10. 12 is abundant. The sum of its proper divisors is greater than 12. And most numbers are either deficient or abundant. So an abundant number is usually one with lots of different factors, and a deficient number is one with not so many factors. So you see that 10 has only 3 factors, 12 has three proper factors, or 3 proper divisors, pardon me, whereas 12 has 5 proper divisors. And so that gives you some idea about whether a number is going to be deficient or abundant. So those are 2 definitions that we have, and you can pick any number. Pick the number 18. Tell me, is it deficient or abundant? Pick the number 22. Tell me, is it deficient or abundant? Try a prime number like 7 or 19. Tell me if those are deficient or abundant. All right, so those are some exercises for you to do. Deficient or abundant. So numbers I've been talking about: 18, 22, 19 was another example. Another prime number, 7, say. So just give those a try. You need to find all the divisors of those numbers and add up the proper divisors and compare with the original number. All right, so that is a kind of a vaguely interesting concept, but something that was of great interest to the ancient Egyptians and consequently to the Greeks was whether a number could add up to itself if you looked at all the divisors. And that number was called perfect. So the first perfect number is 6. 6 is 2 to the power 1 times 3 to the power 1. So its divisors are, according to this table, 1, 2, 3, and 6. So the divisors of 6 are 1, 2, 3, and 6. The proper divisors of 6 are 1, 2, and 3. And miracle of miracles, when I take 1 plus 2 plus 3, I add those together, I get 6 back again. So 6 is neither deficient nor abundant. We call 6 perfect. And that was the name that you find in Euclid's Elements. Euclid talks about number theory in one of the books of the Elements, and he gave the name perfect, at least its Greek translation, to the numbers like 6. Why call such numbers perfect is not entirely clear anymore. We have lost the reason why these were so important. There's a conjecture, probably true, that it has something to do with the way the Egyptians wrote fractions, but I'm not going to get into that. We haven't talked about fractions yet, so I'm just going to leave that topic. You can read about it certainly online. And something called Egyptian aliquot fractions. It's a method the Egyptians used to write fractions. and it's still used sometimes, even in modern mathematics, but because of aliquot fractions, numbers like 6 had a special significance. Anyway, that is the definition of what perfect is. And so the question is, are there any perfect numbers? Or are there, certainly there is 1, 6, but are there more? And if so, what are they? And can we construct them? They were sort of treasured numbers to the Greeks and the Egyptians. So it was very important to them to be able to construct perfect numbers. However, they only knew 4 perfect numbers. And those are 6, 28, 496, which, by the way, is a number on my license plate, and 8,128. So those are the 4 perfect numbers that were known in the ancient world. What I hope to show you in the next few minutes is that given the mathematics that we know now, we can find more perfect numbers. And it's a bit of work, but it's quite remarkable that we, have studied mathematics for a couple of months, and now we know something. We can figure out something that wasn't known to the great ancient mathematicians of Egypt and Greece. All right, so let's first check that 28 is perfect. So 28, we need to find its prime factorization. 4 times 7, 4 is 2 times 2, 7 is prime, 2 and 2 are prime. So 28 has the factorization 2 to the power 2 times 7 to the power 1. That means its table of factors goes, 2 to the power 0, 2 to the power 1, 2 to the power 2, 7 to the power 0, 7 to the power 1. That was 1, 2, 4, 7, 14, and 28. Okay, so proper divisors of 28 are 1, 2, 4, 7, and 14. Let's add those up. 1 plus 2 plus 4 plus 7 plus 14 is equal to, lo and behold, 28. So 28 has that rare property of being a perfect number. I will let you study 496 on your own and 8128 on your own. So show that 496 and 8128 are both perfect numbers. And in order to do that, you're going to have to find a factorization, a factor tree of both of those numbers, and then use the factor tree to write down a table of all the divisors of them, and then add up the proper divisors, and you'll get the number back again. All right, so those were the only 4 perfect numbers known in antiquity. And there doesn't seem to be a pattern to them, but that's just because we don't know exactly how to look at this. So what we're going to do is use a familiar idea to change the way we look at it, and lo and behold, a pattern will appear. So what I'm going to do is use base 2. So we're going to go back, way back in our course, and look at base 2 arithmetic. I'm going to convert the perfect numbers to base 2 representation. All right, so let's get going on that. So 6 I have 6 cubies. I can make 3 base 2 rods using 6 cubies. Now I can make 1 base 2 flat out of 2 rods. And that is my representation of 6 in base 2 is 1, 1, 0, base 2. All right, let's try 28. So 28, I make 14. I make 7. I make 3. And I make 1. So 28 has the representation 1, 1, 1, 0, 0, base 2. Okay, let's try 496. I'm going to need more space for this one. 496. I divide that by 2. I can make, let's see, 250 would be 500 divided by 2, so 248. Again, I can divide by 2, so that'll be 1, 2, 4. I can divide that by 2, I'm going to get 62. Divide that by 2, I get 31. 62. 31 divided by 2, I get 15. Divided by 2 is 7. I got 3. Plus, that's a minus. 3. Get 1. Okay, so that is 496, and base 2 is 1, 1, 1, 1, 1, 0, 0, 0, 0, base 2. Now 8128 is going to be a bit of work, but I'll leave that up to you. You should be able to do it. It'll only take you 1 sheet of paper for sure. The final result is 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, base 2. Okay, so these look not that impressive, but when I assemble them all together, I hope we're going to see a pattern. So 6 is that, 28 is 1, 1, 1, 0, 0. 496 is 1, 2, 3, 4, 5, 0, 2, 3, 4, is 2. And 8128 is 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, is 2. All right, so we're going to contemplate this, try to see if we see a pattern. Well, clearly these numbers begin with a whole bunch of 1s in base 2 and end with a whole bunch of 0s. But in this first one, there's 2 1s and 1 0. zeros. 1 zeros. 28, there are 3 ones and 2 zeros. 496, there are 5 ones and 4 zeros. And 8128, there are 7 ones and 6 zeros. Ooh. Zeros. Okay, that doesn't like me when I get that close there. 6 zeros. There. All right, so yes, we are seeing some pattern here. One thing is that the number of zeros is 1 less than the number of ones. So here there's 2 ones and then 1 zero. 3 ones and 2 zeros. 5 ones and 4 zeros. 7 ones and 6 zeros. So that's certainly something we notice about these patterns in base 2. The next thing you may notice, and if you think about it a little bit, is that the number of ones is a prime number. So 2 ones, 3 ones, 5 ones, 7 ones. And you might want to investigate. Just take a look at, for example, why is this, consider is this number perfect? And that would be 1, 1, 1, 1, 0, 0, 0, base 2. So it sort of follows the same pattern of, say, 4 ones followed by 3 zeros. But it turns out that it's not perfect. Show that that number is not perfect. So you might want to convert that number back into base 10 and use your arithmetic in base 10. It turns out that it should be let me see, times 2 times 4 times 8 times 16. So I'm getting 15 times 16. What is 15 times 16? 16 squared is 256, so 240, yes. I think that's 240. So try factoring that number, 240. Find a list of divisors and show that it is not perfect. So that, at least it gives us some handle on a pattern. And so we may conjecture now the next perfect number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2, 3, 4, 5, 6, 7, 8, 9, 10. Base 2. So again, convert this to base 10. Factor. List of proper divisors. And show it is not perfect. So it looks like our conjecture isn't working out, but it seems like we're so close. Certainly the 4 known perfect numbers do seem to follow this pattern. It's just this one is broken. It doesn't quite work out right. So, if we were just ordinary folk, we might give up here. But we are not. We are becoming math wizards, and so we can now try to show our remarkable math skills to the ancient Greeks and ancient Egyptians, and they would have, I don't know, given us a job on the spot as chief mathematician if you do what I'm going to show you next. That is, there's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Base 2. This is a pretty big number, but you will find that it well, you can convert it to base 10, not too hard. It is a bit of work, but not really so bad. And in the process of converting it to base 10, you should find at least an indication of how it factors, what its factor tree looks like. All these zeros at the end of it actually indicate that there's a whole bunch of powers of 2 in the factorization. So remember, when we add a 0 at the end of a number in base 10, it means multiply it by 10. But when we add a 0 at the end of a number in base 2, it means multiply it by 2. So that means that there's a whole bunch of 2's. In fact, there's 12 2's in the factorization. And then the rest of this number, if you do the necessary work, you're going to find out that it's simply 8191. So this is well on our way toward finding a prime factorization of this big number. And we have to, at this point, figure out, is 8191 prime? Or does it further factor? In order to do that, we need the square root of 8191. It is about 90 and change. So we need to test prime numbers up to 90 as test divisors of 8191. So what I'm going to do is pull up my calculator. This is my special calculator. You probably haven't seen a calculator like this. It's called a reverse Polish notation calculator, but it actually works very well for many math problems. It usually isn't used because it sort of isn't consistent with the way with the way operations are taught in grade school. But it only takes really a few minutes to learn how to use a reverse Polish notation calculator. Anyway, this is what I use, and it's very easy for me to check whether a number is prime. So what I'm going to do is trial division. So I'm going to take 8191, I'm going to divide it by 2, and I get something that isn't an integer. So 2 doesn't go into 8191. Oh, okay, let me fix that. 8191, I got to enter that a few times. Okay, so let's divide by 3. 3 doesn't go in. 5 doesn't go in. Okay, those shouldn't be a big surprise to you if you've been paying attention. 7 doesn't go in. 13, nope, no deal. 17, no. 19, no. 23, no. 29, no. 31, no. 37, no. 41, no. 43, no. 47, no. 53, no. 57, no. 60, say 61. Nope. 67. Nope. 73. No. 79. No. 83. No. 87. Nope. 87 isn't prime. Oops. Anyway, doesn't hurt. 89. No. Okay, so I've done trial divisions of 8191 by all those numbers. So 8191 is not prime. That means that this is our prime factorization of this big number, and that means that I can write down all the factors of it. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 8, 2 to the 9, 2 to the 10, 2 to the 11, 2 to the 12, and 8191 to the power 0, 8191 to the power 1. Here we've got 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and 4096. Here we do all the multiplications by 8191, so 8191. Oh my. You folks are young and strong and vigorous, so you can do all that arithmetic. I'm having trouble doing it in my head. I don't feel like pulling up my calculator again. Well, what the heck, why not? Oops, let me pull up my reverse Polish notation calculator, and I'll show you how easy it is. So 8191. And I like this way, okay. So I'm going to put in a whole bunch of 2's. Oops. Just 2. I'm going to put a whole bunch of 2's in my calculator. And now 8191. Okay. So there. I've got 8191 times 1. I'm going to store that. No good. Oh, what I'm going to do is I'm going to clear my stats there. Okay, put the 2's back in. Okay, 8191. Okay, I'm going to try to use my stats registers here. So sigma plus. Now I'm going to multiply by 2, sigma plus. Okay, this is not working out. All right, forget it. Sorry for misleading you on that. Anyway, what I want you to do is do the kind of irritating arithmetic here and do all the work. There's just a little bit of it. I mean, 12 rows here. And what you need to do is just to keep doubling this number each time until you reach at the bottom whatever this big number is in base 10. And then add up. You're going to have to add up 23 numbers, and you will find that the result is k. So we have just found the fifth perfect number. This number was not known in the ancient world, and there was a search. They did search high and low for it. They never found it. We just found it using some very simple patterns and base 2 representation. So hooray for us. I think this is a great application of both factorization and of base 2. So a combination of things that we've learned in this course. All right, so I'll leave that up to you. I want you to show that this large number, which is in base 2, and in base 10 it is this, is actually a perfect number. And try to find out what the value of that perfect number is. That is the fifth perfect number, and it was unknown in the ancient world. All right, so congratulations, we have come a long way, and I will post one more video about the prime section, and then we'll be done with number theory, and we can move on to a new topic. All right, talk to you later, and stay safe.